Hello viewers, welcome back to video tutorial on AIOS. In this video tutorial, we will be talking about scale testing. We have already two videos recorded for scale testing, and in the part 1 scale test video, we have discussed about a model which is of 23 billion parameter middle-sized model, where we took a magistral small 2506 model, and in the part 2 we have taken a small model which is Quen 3 1.7 billion parameter model, and in this video we will talk about an altogether a separate benchmarking, Perplexity-Scale benchmarking, where a high throughput LLM serving via AIOS will be stress tested. In this tutorial, we'll evaluate LLM orchestration for high concurrency and consumer grade traffic. So this notebook provides a comprehensive overview of high concurrency load testing with AIOS system framework, and generally a standard benchmarking involves local scale performances, but in this tutorial we are doing a stress test for our AIOS blocks against the Perplexity scale demand, where we simulate a massive throughput required for a modern consumer facing AI applications. This system utilizes the tutorial leverages the integrated AIOS metrics system, where we demonstrate how to orchestrate resource effectively, maintaining a high density throughput and enterprise grade reliability. Even our request scales to earn millions of requests, so how we maintain a good throughput and a reliability. So why Perplexity scale? So we know that not all deployments are created equal. So there are based on the requirements, user will do their planning of a deployment, AI deployment. So to evaluate a AIOS system, so we must test against the scale that reflects a modern high demand consumer demand. So we categorize into the scales into 5 distinct tiers, and those tiers are here. So the first tier is a prototype or POC, where you might hit with 1 or less than 1 RPS, and this will be basically used for internal testing or a single user demos with very or no concurrency at all. And next, the tier is a small startup, where early stage startups, early stage apps with a dedicated user basis, where you might get into 1 to 10 RPS. And the third is a medium enterprise, where internal corporate tools or specialized B2B services with hundreds of active users, where you can expect maybe a 10 to 50 RPS. So RPS here is a request per second. And the larger enterprises, where massive global brands like Amazon, Walmart using AI for customer support and recommendation, where you can expect a very high volume of maybe 50 to 200 requests per second all over the globe. So the next the tier is a consumer scale, which is a crazy scale, a hyperscale, where apps like Perplexity, ChatGPT, and Gemini are used by billions of users globally. So that might come on somewhere around 350 to 500 plus RPS, and a sweet spot for us to do a stress test will be somewhere around 300 350 RPS, because to reach this much RPS we require a huge hardware requirement and the cost involved in it. So benchmarking references. So Perplexity AI operational scale. So we have certain data from 2024 and 2025, where you can check these two links, where they are talking about what is the scale that Perplexity operating with. So this was in December 2024, and with the data, if you click on the link, the data that we have is somewhere around 400 to 430 millions monthly queries it is processing, and if we deduct that for average throughput, which is nothing but 168 requests per second. Whereas for 2025 data, where CEO himself has told that they have got somewhere around 780 million queries a month for 2025. So if you deduct that to requests per second, so that will come somewhere around 347 requests per second. So we will test in between these two values only. So our request per second will be in between these two values. So 168 RPS and 347 RPS. So if you think about the tokens throughput benchmark, so again with the same data, so to simulate the Perplexity scale environment, we translate raw traffic into hardware load TPS. So we assume standard AI search pipeline, which is having user input, user output, retrievals, reasonings, citations, all those included, will consume somewhere around 1000 tokens per query. So if you have if you are agreeing to this number, then so for monthly query of 435 million, monthly queries of 435 million and 780 millions, we will end up with the average throughput tokens per second would be 168k tokens per second and 347 tokens 347k tokens per second. Why? The reason being that is, again, average RPS for 435 is 165 million requests per second, sorry, 165 requests per second. If you multiply by 1000 tokens, it will be 168k tokens per second. And for 780 millions, if you the RPS is 347 requests per second, if you multiply 1000 tokens, it will be 347k tokens per second. So this is the token throughput TPS required by the system. To simulate such a high throughput, again, as I told, we require too much of hardware, so we'll come somewhere in the sweet spot. So the values that they have given may be just the peak values. They may not be an average. Average could be an lesser. So they would have again given the bigger number as the peak value only, not the average value maybe. Again, some considerations that we need to take here. So models differences. So whatever the models that Perplexity is serving and what we have used for testing might be different, because again, because of the hardware availability and all. So we choose to do a scale test may not be the same as a Perplexity uses. And token per request. So what is the total tokens? So input plus output plus context plus citations included, so can be different from what we are testing. So Perplexity, it could be this much, so it could be 800 to 1500 tokens per request, but in our test we will be sticking to a 512 tokens per request. So hardware availability concerns for hyperscale testing. So we cannot go beyond certain limitations. Again, the hardware availability, you need to have a dedicated locked in hardware for doing this kind of a stress test, which is a constraints for us, and also the budget and cost constraints. So we choose a very high throughput model. Perplexity can be using a model which is like maybe 8 billion, 70 billion, multiple combinations of model. And also Perplexity, whenever user sends a request, it's not that within one model a request can come. They can internally route to several requests to gather as much as the proper output. They might route it to several models, but in our case we are not doing that. We are just going to have a single call. So this is related to the Perplexity benchmarks and benchmark references. So with this data, we will go ahead. So I'll not explain the data related to scaling, the information related to scaling, resource allocation policy, load balancer policy, autoscaler policy, health check policy. These all are already explained in our previous videos. So the same policies are being used. So I request user to check our previous two videos to understand what these policies are, how they are written, and what is the fundamental idea behind writing those policies, and what all parameters we are using in those policies. I request user to go ahead and check the previous videos. So load testing strategy. So we have taken a smaller model, 0.8b million, recently released Qwen 3.5 0.8b billion model, where we are running with FP8 data type, and it consumes somewhere around 1.7 disk space, and GPU RAM, it might take somewhere around 4.2 to 4.6, and maximum token it can do is somewhere around 2.62 tokens per tokens. And the latency we have seen is for one instance on B200, one instance, it will take somewhere around 0.08 seconds, and this was tested for 256 output tokens and a batch size of 32. So you have a batch size of 32, meaning 32 input requests are batched together and done an inference, and average output token expected is 256 from each request, maximum of 256. And when we tested it on B200, we got a 0.08 as an latency. And for the same batch, if you want to calculate the token generation, so since its batch size is 32, and we got somewhere around 94 to 98 tokens given by the LLM, VLLM, so it will be 32 into 94 to 98. So this will be somewhere around 3136 tokens per second for batch of 32. So to so this is about the model, and we need to understand our library, what library we use. So we have chosen VLLM library. It supports the batching, so not all library supports batching, so you need to choose a library which has a batching capability and continuous batching, things like that. So we have chosen VLLM library, and model splitting capability is also possible in this VLLM. And to define the load testing scenario, we are going with the 300 RPS because we wanted to match the perplexity scale in between. So we have 168 RPS and 347 RPS. In between is 300 RPS. So we have chosen a 300 RPS for our load testing scenario. And this is the total tokens of 3136 tokens is from one GPU, and this B200 nodes will have generally 8 GPUs. So for 8 GPUs, it will be somewhere around 24K to 25K tokens per second. So this is the ideal condition total tokens per second from one B200 node, which is having 8 NVIDIA GPUs. So the next few things are related to how we have created policy, how to deploy those policies, and how to create the blocks. So I'll not go ahead, I'll not go and explain again the same thing. So you can please check the previous videos. So you have a health checker policy, autoscaler policies, and then how to build the Docker. The model codes are again provided in our repo, so you can check the model codes. So model codes are present here. So you can build the Docker, you have to push the Docker to registry, and then you need to register a component, and then you have to deploy. Once the registry component is registered, and then you need to deploy blocks. So right now we are using Qwen 3.5 model, which is a 0.8b, and we are going to create 4 blocks. So why 4 blocks? Because we are going to run our test in 4 different VMs, and we are putting one block in one VM, and internally the blocks will scale, so based on the number of input requests. So each block will scale, and we have given a maximum of 16 pods per VM because we have 8 GPUs, and we have observed that when you have 2 instances of the Qwen model, right, so it's enough, like GPUs will be saturated, so there is no point in creating more and more instances. So that's why we have created maximum of 2 instances per GPU. So since 8 GPUs are there, totally you will get 16 blocks. So 16 blocks per VM, and since we have 4 VMs, totally 16 into 4 pods will be created. So we are going to deploy our models into 4 different blocks. So, and I'm just tagging them with 1, 2, 3, 4. To get the details of the block of the 4 block, you can use this API, and you just have to provide the block names. So just -2, -3, -4 are the 4 different blocks. The important thing is the inference server. What is inference server? Inference server acts like a proxy for passing our inference request to the correct blocks in AIOS system. So you will be knowing the IP of an inference server, but you will not be knowing any details about the block, where the block is available, what is the IP. So that details are completely masked. So you just have the inference request, which is a user facing, and that server will be used as a proxy. And since our input output volume is very high, 300 RPS, so it is very high. So to handle that, we require one inference server may not handle that, so we require a more number of inference servers. So in our testing, we have created totally 9 inference servers, not just because of the reason for that is we need to handle the very high incoming traffic. And again, one other reason is we have some limitations over the number of requests that we can generate as well. So the reason for that is like TCP/IP protocol. So whenever you do an request, so it will basically get into TCP/IP protocol suites, right? Where basically 5 tuple defines your single the request identity. The 5 tuples are basically the protocol, which is a TCP, source and destination IP addresses, and source and destination port numbers. So here destination IP addresses are the inference server IP addresses, source addresses where the client code is running, and where the inference server client is, and the source and destination ports are the ports being used. So the main thing is in TCP/IP protocol, it uses 16 bits for representing a port of input or source port or a destination port. So which means 0 to 655. So since port only whenever a client code generates a request, right? So it has to use some port, randomly generated port within this particular range. So maximum of 65,535 inference requests in flight is possible in a VM. So we cannot go beyond it. So that's why we are creating many inference requests. Like, since we are getting so much of inferences, the 65,535 corresponds to, let's say you are hitting with 300 RPS. The 65K divided by 300 RPS is somewhere around 200 seconds. So within 200 seconds, we might be overflowing this the inference, the ports available. So just to make sure that we, what if within 200 we don't get any responses? Again, after that the client cannot generate because ports are not available. So just to make sure we don't hit into that kind of bottlenecks, we have created many inference servers, and we are running each inference servers in different VMs, so that we the issue of this 65,000 ports, right? So we don't have to worry about. So I have a 9 VMs, and I have a 9 in those 9 VMs I am creating a 9 inference servers. And also for client code as well, so I am not using one single client code. I'll use a multiple client codes, again because of the same reason, 65,535. So you can run the inference server like this. You create a namespace inference server, and you can use each and every YAML file present there by creating kubectl create -f the YAML file, or else you can create 9 inference servers using the bash script present in the folder. So this is the inference server YAML files are available. You don't forget to change your ports or the IP addresses required. So next, once the inference server are up, 9 inference servers, before running the inference server, you just have to check the miscellaneous, because you need to do certain configurations for inference servers. The this is very important, inference server. So you have to change the no file limit to no file to a bigger number. So don't forget to run this piece of code, this commands in your inference server, or else inference server will not start properly, because we have to have a handle very high volume. You need to do these changes. At the same time, you have to do these changes as well. You limits system by default, the limits in the system, what the numbers it will be somewhere around 1024. So you need to change those to some 65,535 in many of the places. So you just check this miscellaneous to configure your all the VMs, be it a client VM. These are required in the client VM, and the bottom thing is required for the inference server. So in the client server, you need a client code. Wherever the client code is running, you have to do all this, and wherever the inference server is running, you have to do this. So once inference server is configured, you can try to run an inference request, which I'll not be doing right now. And anytime if you want to remove the block, you can use this curl commands to remove the blocks that you have started. So let me go to the run and response time and a failure visualization code. So we require to visualize our inference number of inferences and response times, right? So I have created created some codes so that you can see it in Streamlit app folder. So in this folder, all those codes are present here. It is same, it's a little bit modified than previous one. So you use the latest code, and you just have to set up your env. So please put the passwords of a timescale db, username, and IP address of timescale db, everything in this env file, and just run that env file and install the required by this Python code of Streamlit app, and run the Streamlit app in a screen command. And once Streamlit app runs, so it might use some port of like 8501 or 8502. So use that server IP and open that port, and you will see a UI of this sort. So when you run a client code, the client code LLM bench 1.js, which is present in the client code. So the LLM bench 1.js, LLM bench 2.js. So whenever you run this client code using this bash script, right, so it will display a test ID. So you just have to take that test ID, and you need to paste it in the test ID tab, and you need to give your time ranges and then submit. You will get a graph like this. So this is for our current run where you are seeing, right? So it has run from 21 April 16th, 21 in the night time, and it has ran up to April 17th around 4 o'clock, 5 o'clock, 16 o'clock, something like that. So in the graph, initially you are seeing a little bit spike up in the average response time. I'll explain that why again later. And this is the request count over time. So you can see it has started at on 16th 9 o'clock, and it has reached up to 20 million round in the latest data. So the request count failed over time. So it is starting from 9 o'clock, it was 0, and as time progresses, it has reached just 560 or 600 odd, near to 600. So only 600 requests have failed in 20 million input requests. And what is this failures? Failures are basically timeout events. So whenever our code not receiving the inference request, it will timeout, and the timeout that we have configured is 1000 seconds. So if in case inference request is not coming within 1000 seconds, then it will be timeout, and then we call it as an error. So we have seen somewhere around 600 such timeouts out of 20 million requests. And this is the bell curve, the request response percentile graph. So most of the data is focusing in the left side, so which is good, and we have some data in the some right side as well, so 200, 400, 600 seconds as well. And this is when it was happening is during the initial phase of the test. So what is the reason is, whenever we create a block, it will just be having one single pod, and when you start a client code, it will start with like 300 requests per second, and those 300 requests per second will go to inference server. Inference server will pass on it to the block, and block will try to analyze the incoming request, and it has to scale up. So where our autoscalar policies will take it, and it will try to scale the instances. So since you are giving with very high throughput, so the metrics has to reflect those throughput, and then metrics we are taking the average value in the metrics, and then it has to identify, okay, how many instances are required. So it will try to scale the pods one by one slowly. And in doing so, it is not that pod, as soon as pod started, you have the model ready for inference. Since we are using a VLM, it does a lot of optimizations as soon as the model starts. So it will do some sort of compilation and all. So we have seen that it will take somewhere around 1.5 2 minutes. So for 2 minutes, again, you will not be using that model for serving at all. So VLM is simply loading it. So in such cases, you will have a request which is in flight, and it is not being served. So because of that, initially we will see an higher wait time or a response time. So that is the reason we have a spread here. But as time progresses, right, so as like after maybe some 15 minutes, once all the pods needed by this 300 second is configured correctly, all the pods are up and running, you can see a very low throughput. So the issue that we are seeing here is not because of the system, it is because of the model that it takes time to load. So this system uses our system metrics only. Let's say you have an heuristic of your deployment. Let's say you know that from 6 o'clock to 7 o'clock you will get this much of hits, or you have any data like that per day basis, or Saturday Sunday you have some higher traffic. So if you have such kind of a heuristics, you can use that as well to scale the pods advanced, so that you don't have to worry about the metrics data, or you can club both metrics as well as the heuristic data of your previous runs, or your systems, your history demand. So with that as well, you can scale your pod. You can keep the pods in pre, meaning like you don't have to, you can keep it in advance then when the metrics are really reflecting. So you can keep it in advance, so that you will serve the user very quick. So that is one changes we can bring in. But right now I don't have any heuristics or a history of such a requirement, so I don't have that data to create my autoscalar policy. So this is about the results. So let us, since we have run the simulation, I'll just show you the data again, though I have walked you through already. So we have run our test on 4 NVIDIA HGX B200 with 8 GPU per node configuration, and to match the Perplexity-Scale, we have run this test for almost 19 hours. It's a very long time, 19 hours 8 minutes we have run. And in our run, we have observed that an average throughput of 298 requests per second is being what we have pushed and received. So though we have planned for 300, we have received a 298.93 requests per second. So 773 millions is the request per monthly. So token throughput, so we have received somewhere around 119k tokens per second. Though we know that the Perplexity is doing somewhere around So Perplexity is doing somewhere around 168K to 347K, but we are at 116K. So it's again because of not much of hardware. So if we have hardware, we could have definitely scaled it. So we just have a 4 hardwares, B200, totally four 8 into 4 32 GPUs with us for the test, and the total request processed is somewhere around 20 million, 20.5 million, and total failures is 619 failures. So the failure rate is 0.00299, so which is then 99.997 success rate, which is an enterprise grade. So that's it about the result analysis. So we have got a huge success rate, very less failures to nearly 300 requests per second is being served with a total of 512 tokens input plus output, and 119K TPS tokens per second is the generation token. So to know the blocks metrics, if you want to know the blocks metrics, we require a Grafana dashboard. So I have already configured the Grafana dashboard for all the 4 blocks. So to you just have to go to Prometheus, the Grafana dashboard, configure the Prometheus source unit, and then upload the 4 JSON files that we have supplied in the folder. The 4 JSON files are present here. These JSON files, you just have to put it in the you just have to upload those in your Grafana dashboard. So just before when you are configuring a Prometheus, as soon as you click it, you will get an URL, and just make sure that you UID, not URL. In this URL you have a UID. Just replace this in the JSON file. You just have to replace the so wherever you are seeing some dummy so wherever you are seeing Prometheus, so you will have some UIDs. You just have to replace in those panels. So I will not go in detail. So you have Prometheus, yeah, change this to your Prometheus UID. You just have to update the Prometheus UID here. So once you change the Prometheus UID, you just upload that into your VLLM. You can go to home dashboard, and so you can always upload a new dashboards and using the JSON files. So that way you can see the metrics of each and every block. So we have 4 blocks here. I have 4 Grafana dashboards, so you can see here. So this it's last 24 hour data. So as you can see, it is on April 16th, around 21 queue length was a little bit high. It has reached individually like maximum of 1000 for any given pod, and if you sum it up, the at that point of time for the block, maximum 2K queue length was there from for a very short duration of time. So it might be somewhere around like say some 15-20 minutes, because the pods were starting phase. So that's why you have a queue length, but later on, as you can see, the queue length is very minimal, so 8-10 something like that. So you can check for other metrics as well, or you can add many more metrics as well. So the how to run the client simulation code. So we have 2 client simulation client codes, as our input requests are very high in numbers. So we have, just to make sure that we don't end up with any issues of a client code, so we created a 2 client codes, LLM bench 1.js, LLM bench 2.js, and you have to run this to bash files. So let me just open one file. So we are using a package, K6 package, for its simplicity and higher inference request capability. We could have gone for Python, but again we'll end up with again Python GIL locks issues. So we just chosen K6 for, as it is built in Go, which utilizes which is efficient in handling multi-threaded architectures. So this allows a single machine to simulate thousands of concurrent users and hundreds of requests per second within a minimal client-side jitter. So we have in part 1 and part 2 videos, we would have used a Python asynchronous based request, but there the RPS was very less. But here it is, since it is 300, we may not be able to use that same code, so we had to change our client code with K6 package. So how to install K6? Again, it's there in the bash file. So just 4 lines of code. So you just run this file and you will get a K6 in your VM. And you need to make sure that you have handle the ulimit issues, to which basically you will end up with again too many open files error. if you have not configured the U limits properly. So you just check the miscellaneous section which I have explained from this to step 5. Step 3 you have to do it in your node, the client node. Then to run the code, you just have to create 2 screen commands and run the bash files, and you just don't forget to change the inference servers and DMA log endpoint, because I would have given a placeholders and you just have to change those values. So you create a screen command and run the bash script and control ID for coming out of the screen. And similarly for the client too, again you run it in different VM because of issues that I have told, like 65,000K requests only possible in-flight requests. So you have to run it in 2 different VMs. So let us go to the code. The client code, where the important is the inference servers here. This piece of code will generate an test ID. So use this test ID. As soon as you run the code, it will print a global test ID. So you just pick the test ID and put it in our response endpoint, like Streamlit app endpoint. So test ID is created. Then we have inference servers. So we are creating totally 9 inference servers, right? So I'm dividing 4 inference servers for one client and 5 more inference servers for other client. So once you have the inference, so you can use the master node because these are node port. So the same IP can be used there, and these ports are exposed. Just make sure that your VMs, the inference server VMs has they can open the ports the required. And I'm just changing this IP only. You just have to change the IP because all the inference servers are in node port. So one IP change is required in this piece of code. So then a DMA endpoint. So for one client I'm using one endpoint, and for other code I'm using a second endpoint. So since you have to run a DMA also, DMA basically for logging the input output request response times. And since it's a very high throughput, input is 300 requests per second, you should not lag. I mean, this endpoint also should not lag. So just to make sure that I don't lag, I have created a 2 log endpoint. Or else you could have created some sort of in memory or like you could have disconnected from this code by pushing it into some sort of a queue. That also can be done, but right now we are using a DMA log endpoint. So how to run the DMA endpoint, I have again I'll explain in the later section. So here total simulated users 40,000. So what is this 40,000? Again we need to go back to that 65K. Since we can maximum open of 65K port, right now I'm restricting myself to a 40K only. I will not go beyond 40K. It means my client code, it can generate maximum of 40,000 requests at any given point of time. It cannot generate more than that. So if at all it is generating, it will not generate at all, because it will be it's the users, the simulated user is nothing but a virtual user they call. So when it reaches 40K, it cannot generate any more requests. So your RPS input itself will come down slowly. So just to make sure we don't go beyond that, near to that 65K, we have just make sure that it reaches to 40,000. So beyond that it should not go, and if it is going beyond, it will not go beyond first of all, and it will not generate any more requests. So you initial time, right? So you will see as soon as you run the script, I have seen that this will go somewhere, the virtual users will go somewhere around 31,000, 32,000, 35,000 and all. And once all the pods are up and they are start delivering the responses, then that number will slowly come down. So at the end, I mean, you will see on an average 500 to 700 or 1000 views on an average. That is what I have seen in my experiment. So going this number, the virtual users reaching to 35,000 is an initial phase, and once initial phase is crossed, it will stick to somewhere around 500 to 1000 virtual users. So since I have 2 clients, each client will start with 150 requests per second, and this means 150 plus 150, you will get somewhere around 300 requests per second from together. So this I'm not using it, and the 150 requests per second I'm running it for nearly 1380 minutes, which is somewhere around 23 hours. So for 23 hours I am delivering with the 150 requests per second. and post that for 30 minutes I was trying to reduce the number of requests. So I have not run this test for complete 24 hours, only 19 hours I have run, and after that I have stopped it as I got required data. And the main code, the first client code uses a 2 model and the second client code uses a 2 other model. Similarly, like inference server, the first client code uses a 4 inference server and second client uses a 5 inference server. Similar to that, you have a 4 blocks. I am separating 2 blocks for a one client code and 2 blocks for a other client code. Then this is basically hitting the input request. This is the payload data. So right now I have given the same prompt for all the inference requests, but you can change it like how we did it in previous section, where we read all the questions that we have in some text file or JSON files. We read all the questions and we were changing the questions every time. That also we can do, but right now in our test I have created the same prompt. So this was our prompt that was tested with, and we have given a timeout of 1000 seconds. So if the response doesn't comes within 1000 seconds, it will time out and it will throw it as an error. So that error is what we have captured in the graph as an error or a failed responses. And after that, once a response comes, we'll log the data to DMA. So DMA will dump the data with this kind of metadata: start time, end time, and response time. All those informations along with the test ID, block ID, session ID, sequence number, all those data are dumped into the DMA DB. And since DMA DB also can go into some issues, right, because of too much of input output requests, we have some iterations, some 2-3 loops it will try to do, and maximum attempts being 3. You can increase it so that it will make sure that it dumps the data. So we have seen some issues sometimes, so it's better to run with some attempts. So this is the simple piece of code available in the client side. So these 2 client codes you have to run by changing. Just don't make sure that you need to change this whatever the DMA log endpoint and inference servers are there, right, that you need to change it. So I have explained about the VU concept, virtual users. So again, initial times you will have more views being created, and later as time progresses, lesser views will be, it will not use all the views, it will use the lesser views. So this is the DMA data, the data structure, and this was a screenshot when I stopped my test. This was the screenshot. So the left side is a client 1 and the right side is a client 2. So in the left side, the client 1 has run already for 10 millions. In that 561 was a failure, and in the right side you have a 10 more millions with 56 as a failures. So the iterations, as you can see, it is 149.51 requests per second, and this is also somewhere around 149.47 requests per second. So this was generating 10 million, this was generating 10 million, together 20 million input requests we have generated. So some more time was spending. I have interrupted because we kept for configuration of 24 hours, but I have interrupted around 19 hours, 11 minutes or so I have interrupted the test. So this was the test result from the our K6 client app. And how to run the DMAs, as I mentioned, we require 2 different DMA endpoints because of high input. So you just copy the DMA code to 2 different VMs. So DMA endpoint, you can just copy this folder to 2 different endpoints, and you just have to run the bash file. So make sure requirement.txt is not required. You just have to run the just install the requirement.txt and run the bash file, and whatever the passwords and username for a timescale DB is required, you just have to change it in the config.yaml and run the bash run.bash. So that will start the DMA, and make sure that this DMA is running in 2 different servers. So CPU servers, not the GPU server. GPU is not required for it. And so once you have the 2 different IPs, just place it in the client code and run the client code. And when you are running one client code, as soon as you run the client code, it will put into the test ID, copy the test ID and go to the second client code and put the client code, the test ID in the second client code. I'll just show you that, the client code. So yeah, you just have to paste your test ID here, so that when this test is running, it will, though it is hitting the same blocks, when it is dumping, this test ID is used to dump the data into the DMA properly. So the test ID, so with this test ID only we are trying to pull the data from the timescale DB and project it in the Streamlit app. So that one change you need to do manually. So whenever a first client is over, copy the test ID, give it to the second test client code and run the second client code. So that's about the DMA, and miscellaneous I have already explained what you need to do it in the system. So that's it in the video. We have tried explaining what is why we have chosen Perplexity-Scale, why we are not chosen Gemini or ChatGPT is because of again hardware constraints and cost involved in it. So we tried taking some metadata, so some data or knowledge about Perplexity, and we tried replicating our scale test in our AIOS system with the Perplexity-Scale as a benchmark figure. So that's it. So thanks for watching, and keep supporting us. Thank you.